session, we have a talk that's going to be jointly given by Jonas Kamminga Dorian Rudolph, and it's going to be on this pure state consistency of local density matrices problem, and I'll let them take it away.
Thank you. Yes, so good afternoon, everybody. My name is Jonas, and I will be talking about the pure state consistency of local density matrices problem. This is joint work with Dorian Rudolph, who will be taking over halfway through from me. So let's jump straight in with the definition of the consistency of local density matrices, or CLDM problem. In this problem, we are given a set of local density matrices, sigma 1 up to sigma m, and we are asked whether there exists some global state that is consistent with these density matrices. What do I mean with that? Well, I mean simply that the partial traces of this, so the reduced density matrices of this state rho agree with these sigma i's. This problem shows up in physics, and it was shown in 2006 by Liu that is QMA complete under Turing reductions. Later, it was also shown that two variants of this problem, the bosonic and fermionic n-representability problems, are also QMA complete under Turing reductions. And finally, in 2022, Broadbent and Grillo showed that the CLDM problem is QMA complete also under CARP reductions for k is 5. So the size of the density matrices is 5. In this work, we look at the pure CLDM problem. This is a variant of the CLDM problem where we now ask for, is there a consistent state that is pure? And this problem is still QMA hard, but now we don't know whether it is contained in QMA. In fact, the best upper bound is QMA 2, and the best upper bound to that is NEXP. So it could be that this pure CLDM problem is as hard as NEXP. And it's been an open question in the field for a while now whether pure CLDM is a complete problem for QMA2. So in this work, we study how hard exactly is this pure CLDM problem. And before I state our results, let's start with a little bit of a warm-up, namely by showing how CLDM is contained in QMA. So the idea here is to use tomography. So we have some state rho given by the prover, and we want to check whether it's consistent with these density matrices. And we simply check whether it agrees locally, whether the measurement statistics agree. So we pick some random sigma I and some Pauli measurement p on Ci, and then we just verify that the trace of p sigma I is equal to the trace of p rho. And note that the trace of p sigma I can be computed classically because sigma I is a very small matrix. And the trace of p rho we can estimate, but to estimate this, we need many iterations. We need to do many measurements. And this can be a problem, but the solution is very simple. We just ask the prover to give us many copies of the state. And you might be worried, however, that the prover could entangle these copies between each other to trick us into believing that there is a consistent state while there is actually none. But in the mixed case, this is no problem. The reason for that is that there will be no operations across the copies, so there's no tricking that the prover can do. But in the pure case, this is a problem. And why is that? That is because it could be that the prover gives us some global pure state consisting of many copies, but the copies are entangled in such a way that the actual individual copies are mixed states. And we don't know how to check purity in QMA. So we don't know to check whether these local copies are actually pure or not. So to find a home for the pure CLDM problem, we asked ourselves, well, what if we have a class where the verifier can somehow know the acceptance probability without having to do many measurements? And a class like this was defined in 2003 by Aronorov and Regev. It's called Super QMA. And here we have some super verifier, which is just a collection of circuits together with targets and accuracy parameters. And in the yes case, there exists some mixed state rho, such that for all I, basically our predictions are correct. That means that Vi accepts the state rho with probability at most s away from Ri. And in the no case, there is a delta fraction of the i's where our prediction is wrong. So we have three parameters here. We have m, which is the number of checks or the number of circuits in our super verifier. And then we have epsilon and delta, which are just precision parameters. So Aronorov and Regev showed that this is equal to QMA when we have exponentially many checks and polynomial precision. But crucially, their proof relies on the mixedness of the provings of the row. So we asked, well, what if we make the state rho pure by promise? Then, by the algorithm I sketched in the warm-up, it would contain the pure CLDM problem. So this leads us to the definition of pure super QMA, where we again have a super verifier, but now in the yes case, there is some pure psi for which that fulfills all our predictions. And in the no case, for all psi, our predictions are wrong for some delta subfraction of the i's. And again, here m is the number of checks, and epsilon and delta are the precision parameters. And as I said before, the pure CLDM problem is contained in pure super QMA with poly many checks and 1/poly precision. And hence we define pure super QMA to be this class. Note that the QMA equality for the normal, so the mixed super QMA already holds with exp here. So exponentially many checks. Whether pure super QMA is also equal to QMA, that is still an open question. We have not been able to resolve. So what can we say about this new class, pure super QMA? Well, the first thing you might ask is, well, if it contains pure CLDM, can we also show that pure CLDM is complete for pure super QMA? And our first main result is that yes, we can indeed. And our proof for that is a modification of this CLDM completeness problem proof for a QMA by Broadbent-Grillo. We make some more modifications to make it already work for RDM size k is 2. And we also make some modifications to make it work for the pure representability problems. As a corollary to these latter modifications, we also get for the mixed version, so the normal CLDM problem, that it is already QMA complete for k is 2 as opposed to k is 5, which was proved by Broadbent and Grillo, and that the n representability problem is also QMA complete under CARP reductions. So I will not go into the proof because I don't have the time, but let me sketch one thing that might be of independent interest, and that is that we can find a canonical form for this class pure super QMA. So recall that we had these R's and these S's, the targets and the accuracy parameters, and they make this whole class a little bit messy. So what we want to do is just replace all the S's with 0 and all the R's with a half, making the class look just slightly nicer. And we show that we can do this, and the proof idea is that we can shift the acceptance probability of the verifiers to 1/2 by adding random coin tosses in a smart way, and that we can ask the prover to send us correction terms in superposition to make sure that the accuracy parameters can also be set to 0. So with that, let's continue with how pure super QMA relates to the zoo of complexity classes out there. Well, firstly, QMA is trivially contained in pure super QMA. We also show that pure super QMA, even with exponentially many checks, is contained in QMA2 as long as the precision is polynomial, and that pure super QMA with exponentially many checks and exponential precision is equal to NEXP. So this already gives us the idea that pure super QMA might be between QMA and QMA2, maybe strictly between. And as upper bounding QMA2 has been a major open question in the field, we ask ourselves, well, can we upper bound super QMA? And our next main result is that, yes, we can indeed. In fact, we show that pure super QMA with polynomially many checks and any precision parameters, even 0 exact precision, is contained in p-space. As a corollary, we get that the pure CLDM problem with any precision parameter is also contained in p-space. So what does this mean for pure CLDM versus QMA2? Well, we argue that this is evidence against its completeness, or at least a barrier towards proving hardness for QMA2. And why is that? Well, as you might know, QMA2 becomes equal to NEXP when you make the precision exponential. But as we show, pure CLDM remains in p-space, even for exponential or even preciser precision. And as p-space is equal to NEXP is deemed very unlikely, this means that any proof of QMA2 hardness of the pure CLDM problem needs to fail in the precise case, providing a barrier against these proofs. So let me now sketch a little bit the diagram of the complexity zoo. So we have here pure super QMA, the new class that we introduced. It contains QMA. It's contained in P-space and in QMA2. The relation between P-space and QMA2 is still a major open question, but both of them are contained in NEXP. And note also that with even exponentially many checks, we still get pure super QMA in QMA2, but not in P-space. And I'll hand over to Dorian, who will talk about the upper bound.
Thank you. Yes, so I will give a brief sketch how the containment in P-space works. So first note that the pure CLDM problem is not a convex system. And so we rely on root finding techniques by representing the problem as a quadratic system over R. And so consistency is equivalent to a quadratic system in the state psi, which looks like this. So we have the partial trace of psi is sigma I, and sigma I is the reduced density matrices that we are getting as input. And we also have normal unit vector constraint. And so note that we write psi with separate variables for the real and imaginary parts, so that the complex conjugate is just a linear expression in our variables. And note that if we have a constant local density matrix size, k equals O of 1, then we have a polynomial in n, the number of qubits, number of quadratic equations, and 2 to the n plus 1 variables. And now we can add slack variables to check for approximate solutions. So now we have a new problem, which on the face of it seems much harder than our original problem. So how do we efficiently solve a few or polynomial number of quadratic equations in many or exponentially many real variables? But this has been studied in sort of the field of real algebraic geometry by Grigorevich and Pasechnik. And for this, we introduced sort of their system, which we call the GP system, which is a polynomial system, P of Q of x equals 0, where x is a vector of real variables, and P is a polynomial that takes in m variables and gives out one value of degree d, and then Q is a sequence of m quadratic polynomials that take in n variables, and here n is 2 to the O of m would be the number, so the dimension of our state roughly. And Grigorevich and Pasechnik show that GP system can be solved in exponential time. In this work, we improved this to P-space using the characterization of P-space NC-poly, which is parallel polynomial time or circuits of poly depth. And note that, so we have this characterization with these two polynomials, but we could easily solve a more conventional quadratic system, and we just have some quadratic formulas Qi with some target values Yi, just by summing all the squares of the differences. And so then our corollary is that the pure CLDM problem, which is contained in pure super QMA, is contained in P-space. So sort of brief interlude. So we ask, can GP solve QMA2? And this is not obvious, because the easy way to do a cubic separability constraint, so to do a separability constraint is cubic. So it would look like this. And so it's just as the same size equal to the tensor product of two states, psi1 and psi2. And a different way would be to use the Seeger variety, but that takes quadratic number and the dimension constraints. And yeah, so as a side note, we observed that variant of GP systems with cubic Q is next part, following the next hardness of precise QMA2. And now let's go back to the proof. So the general idea of Grigorevich and Pasechnik was to reduce solving P of Q of x equals 0 to what they call pieces. And each piece is a polynomial system in only O of m variables. And the idea was to the observation that the critical point equation is linear in x and q of x. And it turns out that adding infinitesimals, you can guarantee that sort of the rank of this linear system is n minus O of m. So the system is almost full rank, and if you only effectively have O of m degrees of freedom. And this gives us, for these pieces, n to the O of m candidates for invertible submatrices. And so each piece is sort of the set as epsilon, and in the limit, they show that the pieces intersect all connected components of the solution space. And yeah, so as mentioned, they show how to compute these limits in exponential time. But here we need to compute all these the limits to these pieces in parallel polynomial time. And for that we write, so you can write the limit of a set or a sequence of sets as epsilon like this. Notably, this is sort of a sentence in the first order theory of the reals, and first order just means it's a user's quantifiers. So we say that some point x is in the limit of the s epsilons if for all radiuses r there exists some epsilon 0, such that for all epsilon smaller than epsilon 0 there exists some point y in the set s epsilon that is sort of in the r ball around x. And turns out that Renninger showed how to solve these first order theory of the real sentences efficiently in parallel polynomial time. And this gives us the ability to solve all 2 to the poly m pieces in parallel. And we know that a solution, i.e. a consistent state, exists if and only if at least one of the pieces is non-empty, because the pieces intersect all connected components of the solution set. And so now that we show we can decide in P-space whether there exists a solution, can we also compute some consistent state? And for that, we need to approximate some x such that P of Q of x is equal to 0. Yeah, so recall this formula. And in fact, Renninger also shows how to compute approximate solution to first order theory of the real formulas. And the first problem that we need to deal with is that his algorithm only computes poly m entries in poly time. But recall we have an exponential number of entries. And so our solution is to just compute the different amplitudes of the state in parallel. But then we have a different problem. So then how do we make sure that each of these systems we solve in parallel will solve for the same state? Because there could be multiple solutions. And yeah, so the solution for that is to compute an additional set of constraints that uniquely identifies a solution, which Renninger also shows how to do. And so let's go to some applications of these systems. So, I mean, yeah, so we hope that these GP systems are powerful too, and hope that it's a good candidate to solve hard quantum problems in P-space. And so we have some more applications in the paper, but one I'm presenting here is so to put some version of QMA2 into P-space. This is the version that was also analyzed by Xi and Wu. And here there are 2 parameters, epsilon and r. And epsilon is a promise gap, and r limits the number of gates that can act across multiple registers. So let's say 2 local gates. So a gate that acts across multiple registers acts on both proofs or on one proof and an ancilla. And we show that this version of QMA2 for any epsilon and a logarithmic number of the cross register gates is contained in P-space. And this improves upon Xi and Wu's result, who had the analogous statement for inverse polynomial promise gap. And so let me conclude with some open questions. So first, we conjecture that the class pure super QMA is strictly between QMA and QMA2. So we would like to show oracle separations, but this again, we run into the issue of the disentangler conjecture, which has not yet been proven. And we also are interested in what can we say about inclusions with just a constant number of checks. So pure super QMA k, is it strictly contained pure super QMA k plus 1? And here, k is a constant. And so finally, does the power of QMA2 come just from purity checking? So here we have this version pure super QMA x poly poly, and not the x is the number of checks, and poly is the promise gap. And we have not shown containment in P-space for this version. We only showed it for a polynomial number of constraints. So it will be interesting. This is already enough to capture the full power of QMA2. And yeah, so thank you for listening. And I would like to mention that I'm expecting to graduate at the end of this year, roughly, and I'm looking for a postdoc. Thanks again.
Thanks to both of you for the great talk. So we have a couple minutes for questions. Actually, can I start with a question? So, have you guys? So one thing that QMA2 can do is like you can have proofs for SAT formulas that are shorter than linear length. Like, have you thought about whether it's possible in this class?
I haven't thought about that. But yeah, it sounds like a good question. So I think, I mean, in these proofs, I mean, I guess it's sort of like a Bell QMA formulation. I don't know if that has been studied.
Mm-hmm. Mm-hmm. Makes sense. Thanks. Do you wanna...
No, yeah, just that we haven't really thought about this, but it's a good question.
Cool. Okay. Other questions in the audience? Oh.
I guess my question is, why do you think the classes are different? Like, why do you think pure super QMA is different than QMA? Do you have some intuition why that might be true?
Yeah, it just seems like the purity testing doesn't seem like something that you can do with a quantum circuit, like without having multiple copies.
So you mentioned that with poly many checks, it's in p-space. With exponential many checks, it's in QMA2, but not in p-space. Can you comment on this? Kind of like what breaks down?
Well, so recall that the runtime is sort of polynomial in the number of checks, and this parallel polynomial time framework. So it's the number of checks increases, and also our parallel runtime increases. So that's really the threshold. But for QMA2, as long as we have this inverse polynomial promise gap, it suffices to just pick one of these checks at random and perform the check, and then with one over poly chance, we will just detect the no case.
I'm just wondering, so the way it's presented on the slide, the conjecture, it seems to suggest you think you have equality for exponentially many checks. So I stepped in a bit late, so maybe you could remind me what the number of checks means. And also, I'm curious as to if you think it's more likely to be equal to QMA2 as opposed to conjecturing a strict containment even for exponentially many checks.
Sorry, what was that about the first question again?
Yeah, like what does it mean, the number of checks?
Yeah, so we have a pure state, and then we sort of have a check. Or you can also think of it like a constraint. So it's a quantum circuit that you run on your pure state, and then you wanted to have acceptance probability exactly 1/2. And we can have many of these different checks so like we have sort of an array of circuits, and each circuit should have an expectation value of exactly 1/2 to accept. And so in QMA2, we can handle an exponential number of these different circuits from which we could pick one at random and then simulate it. And yeah, so regarding equality, yeah, I don't really have an intuition. Maybe Jonas could say something.
So, yeah. Well, there has been some other work on QMA2 that sort of suggested that like purity testing is all there is to QMA2. So one way to sort of formalize this intuition with our pure super QMA class would be to show this equality. Whether or not I don't want to state that it as a conjecture that they're actually equal, but as an open question whether these things can be.
Sure. What's the intuition? Like, what are the works that give intuition that purity is all there is?
I believe the work with QMA2 with internally separable proofs by, I believe, the gentleman in front of you, but yeah.